All right. Is this working? Yeah. Here we go. All right. Hey, thanks everyone for joining us tonight. I really want to give a shout out to Viv and Arjun who put together this whole event. I'm basically just showing up and talking. They are the ones who did all of the hard work. But let's get started. So the goal of the next like 25-ish minutes is I want to give a high-level overview of what zero-knowledge proofs are, what you can build with them today, and the next talk after me is actually going to like show you some code examples, really get into the weeds. So this is meant to be a high-level overview, and let's jump into it. So the first thing that I want to like correct as a misconception is that the way that blockchains work right now, like Ethereum and Bitcoin, are probably the most dystopian thing you can imagine. If you send someone $1, they know all of your assets, they know all of your trade history, and it's really crazy to imagine that like the future financial system is going to work this way. There's this idea of pseudo-anonymity, right? You have something that's like a private-ish address, but once that's connected to your real identity, it's there permanently forever for everyone to kind of like look into the details of everything you've done. So let's give an example of this. You see this address right here. It looks kind of private, but this person decided to buy an NFT and post it as their Twitter profile picture. So does anyone know who this is? It's Snoop Dogg. Right? So now we can like dive into his history. We can see that he's transacted over $31 million. He currently has over $2 million. Like I can give you timing. I could build his social graph. And if I did this, I would be a $1 billion unicorn named Chainalysis, who sells this data to governments. They sell it to private industries. It creates so many problems, right? Maybe Snoop Dogg's like a really smart NFT investor. Well, now I can front run all of his trades forever, and there's nothing he can do. If he moves money to another wallet, right, I'm still following him. So I'll talk about that in a second, but with mixers, like there are weaknesses. So we'll dive into it in a second. Like Tornado Cash is a zero-knowledge proof, right? So that's one of the applications. So how do we actually get privacy on blockchains? Zero-knowledge proofs are not the only way, right? You hear a lot about zero-knowledge proofs, but there's also secure enclaves. So this is things like Intel SGX. The way that your iPhone stores your Face ID is actually like in a secure chip. Now, the reason we can't use these systems, even though some people are, for blockchains is because they have the self-defeat problem. They are vulnerable to someone attacking their own chip. So they don't work for trustless systems. The next approach we have is zero-knowledge proofs. And zero-knowledge proofs you can think of as secured by math. So there could be problems in the implementation, there could be problems in the code that people write, but they have theoretical guarantees. And as long as our assumptions hold true, we can be confident that these are safe and they're private. And this is like the bleeding edge of what's currently being implemented right now. And the last kind of step is fully homomorphic encryption. This is the future. So this is like the most advanced version of cryptography where you can have entire programs, everything encrypted, multiple parties interacting. And the reason no one uses it right now is because it's about a factor of 1,000 to 1,000,000 times slower than zero knowledge proofs. There are people working on making these more practical, but it's still very academic right now. So if we think about like what is a zero knowledge proof doing, it's really basic. So the way that Ethereum works is you have a function, you have some inputs, and you have some outputs. And the way that everyone makes sure that you did the right thing is they just all run the function with the same inputs, and they make sure they got the same outputs. And then they vote on it. And the future of zero knowledge proofs is you can now have encrypted inputs and encrypted outputs. And you also generate a proof that people can verify to ensure that these inputs and outputs were generated in a valid way. So they're encrypted, you don't reveal them to other people, they can be given to everyone, and it's as safe as any other encrypted data. So, like, how does this actually work? Um, the answer is a lot of complicated number theory, but I want to kind of like build up to that intuition. So the first thing that you do is you take a problem and you formulate it into a hard problem. And then because you were able to formulate it to a hard problem, you prove with a high probability that you know the answer to that hard problem. And the verifier then can check and say, okay, he knows with high probability an answer to that hard problem. So we're going to give like kind of a simple example of a zero knowledge proof. I don't know about you, but as a kid, sometimes these were challenging to me. And where's Waldo? There's like this guy in a red hat, red, white striped sweater, hiding somewhere in this image. He's not under the text. I'm not that cruel. And, you know, I would like struggle with these. They can have really big ones. And how can you be sure that there's actually Waldo somewhere in this photo? Right? Like how could I prove to you that Waldo's in this photo without telling you exactly where he was? Oh, don't tell anyone yet. I'll release the slides later. But this is actually how zero knowledge works, right? So if the picture is too small, it's too easy. So like what the math is doing is making this picture like trillions of times bigger. So what I could do to prove that he's somewhere in this picture is I could get an even bigger sheet of paper. I could cut a Waldo size hole in it. I could line up that image secretly behind it to just expose where Waldo was. Because you didn't know the alignment of how that picture was set up with the hole, you can be sure that he's somewhere in here, right? He's somewhere there, but you still don't know where he is. And this is what zero knowledge proofs are doing. And that unless you already found it, it probably didn't help you that much. So in terms of like, how does this turn into actual programming languages and real math, right? Like, how do we actually do that? The simple answer is that there isn't one. This is an active area of research. There are many different schemes that have many different cryptographic primitives, and there isn't really a unified consensus on the best way to do this yet. Generally speaking, what you're doing is creating an arithmetic circuit. So you can think of like every circuit element as like multiplying or adding numbers. And you're proving that you kind of know a solution to that circuit. And to just give you an idea of some of the complexity, this only goes up to 2019. It's like exploded, and most proofs are kind of variants at this point. But I want to take a second and just kind of like point out what's important, right? How do we judge one proof system as being better than another? And some of the most important parts are like the prover runtime. How long does it take to generate a proof? Are you able to generate a proof on a phone, or do you need a supercomputer? How long does it take to verify, right? So the one is constant time. If you're familiar with like asymptotics, that's what these are. Basically, lower is always better, right? And if you can verify things in constant time, that's a huge advantage. The proof size is another really important thing, right? If you're storing it on a blockchain, then the size of the proof needs to be constant because blockchains are not great at handling like dynamically sized data. Another factor is the trusted setup. There's an idea where you can make something a lot more efficient by having things like a ceremony. I'm not sure if you guys are familiar with like the KZG ceremony happening in Ethereum right now. You can go and contribute to it if you want. You might get an NFT later. I don't know. And like, is it updatable? Can you update that ceremony later? Aleo uses the Marlin system. It's actually a variant, but you can notice that it has really nice properties. The biggest is that the proof size is constant. So this means no matter how complicated your program, no matter how difficult of a zero knowledge proof you're implementing, you're always going to have a constant time proof. So let's talk about some of the zero knowledge proofs that exist today. Probably the most famous are Zcash and Tornado Cash. Zcash is like Bitcoin, but private. So unlike Bitcoin, where everything is pseudo-anonymous, right? If you look at section 10 of the Bitcoin paper, it's labeled privacy, and it says, well, we think like pseudo-anonymous is pretty good, but whatever. It wasn't actually possible to implement a private Bitcoin until 2015 when Zcash was invented. Tornado Cash was another popular application of a zero knowledge proof, and also a great example of why we need to build private L1s. The Tornado Cash developers in jail. Zcash you can buy on Kraken. And for Cloudflare, these have applications outside of cryptocurrencies. I don't want you to think that this technology is only useful for crypto. It's useful for any setting where you need to prove something, maybe like an identity, and you don't want to give details about it. And like a really simple example of a zero knowledge proof most of you are familiar with is like a key signature, sign in. So right now, when you sign into a website, you give them your password. That's kind of concerning, right? What if you use the same password multiple places? They have your email. So what if instead you prove that you knew a password, right? And that's all a key signature is. So a key signature is just saying, hey, sign this unique message, and you can prove that you know the password without revealing it, right? So that's like a super simple example of a zero knowledge proof. There are a lot of limitations though, right? So I don't want to like overpromise. Proof generation is hard. It's hard to do operations over encrypted data. It can be pretty expensive, but the rate of acceleration is crazy. And we think that these are like actually practical systems now where you can do things like create light clients that you can run on your phone. This wasn't possible like 2 years ago. I really got to click through for each of these transitions. All right. So I'm just going to kind of group these up. So a big thing is like privacy leaks. Just because you use a zero knowledge proof doesn't guarantee privacy. So a really common example is Tornado Cash. To describe what Tornado Cash is you could basically deposit Ethereum into a smart contract, use a zero knowledge proof to withdraw it to another address. And no one would know that those addresses were, linked unless you did it too quickly, right? If you deposited really quickly and you withdrew really quickly, or if you deposited a certain number of coins. So they had to do fixed amounts of like different pools. And if you did the same, if you did like 67 deposits and then 67 withdrawals, they know it's probably you. And over 50% of Tornado Cash, like probably higher, but at least 50% of Tornado Cash transactions have been statistically defeated. So it's kind of like another reason to create an L1 where you have privacy by default. And another big, really big like problem that people don't understand is zero knowledge proofs do not solve every problem, right? You can't do every sort of program. And the most simple examples are like swaps and escrows, right? Buying an NFT is like a swap. Simple escrows aren't possible. So we're going to talk later about how do we get around some of these issues, right? How do we build systems that are private but require public state to do anything interesting? And this is kind of like what was the inspiration for Aleo. So this is a really simple graphic. It's just you can do, Zcash is private Bitcoin, Aleo is private Ethereum, right? You have the programmability of Ethereum, but you have the ability to maintain privacy, which we think is like, you know, you really want to ask yourself like very deeply if you're introducing like another blockchain, like why? It's like, are there enough blockchains? Probably, right? Why would you want to create another? Is like the TPS higher? Like in all honesty, like this sort of privacy technology, it's going to have wide-ranging applications outside. It's like fundamental advancements in math that are being applied to computers, and it advances technology far outside of the scope. And we're lucky enough that cryptocurrency has been a way to advance this research much faster than we would advance it without. So kind of like to just summarize what Aleo is, it's a proof of stake blockchain, and it validates zero knowledge proofs. So instead of like submitting all the details of your transactions, you submit a zero knowledge proof. And it also has a high level programming language. Pranav from the Aleo engineering team is going to take you guys through some code, give you some examples, show you how to build your own programs today. And it leverages public state plus ZKPs so that you can do basically everything Ethereum does, but maintain privacy. So another, like this first point of preserving the anonymity set, I think a really reasonable question is, why don't you just launch Aleo as like an L2 on Ethereum, right? Why isn't it just like another layer on top, like be an ETH maxi? And really, privacy comes down to this question of like the anonymity set, which is the number of people you could be confused with. If I'm the only one using Aleo, if you see an Aleo transaction, it was me, right? So when you interact and you integrate with a public chain and you can see all the flows in and all the flows out, it really decreases the size of the anonymity set. So you only have one choice, which is to do things slower, right? So that you can kind of be grouped in with other people. And this was the downfall of Tornado Cash and why it was so easy to break. Having first class support for ZKPs is really important too, having a high level programming language. Because honestly, if I have to explain this to every single developer who uses Aleo, Aleo is not going to get anywhere, right? It has to be simple. There has to be technology that you just trust that it works, right? And a big thing to understand, like you've maybe heard the word ZK EVM, things like different L2s building it for scalability as opposed to privacy, and that can be kind of confusing. Zero knowledge proofs have two properties. They allow you to be private and they allow you to be succinct, right? So most of the projects you hear about using ZKPs are actually using the succinct property. You're submitting your transactions publicly, but you're submitting them to a centralized proof generator who then orders them and then puts them on a public blockchain, right? So if you hear about like a ZK EVM, it's almost guaranteed to not be private. The one counterexample is like Aztec, which is another really cool project that you should check out if you're interested. So given that like we have ZKPs and we have public state, how do you actually do things privately, and how do we make this user experience as seamless as possible? So I'm building like the Leo wallet, which is the thing that we're hoping like normal consumers interact with, and we don't want to expose them to any of this complexity. We want this to be simple. We want this to be easy, but we also want it to be privacy. And we're trying to build like the first real private programmable wallet. So the way that you do this is use an HD wallet. HD stands for hierarchical derivation, which means that you have a single seed phrase and you can get as many wallet addresses as you want. You do public transactions with single use addresses, and then you fund them with where you're holding your main assets. So let me show you, for example, how you can buy an NFT privately and how Snoop Dogg should have protected his identity from me. The first thing that you do is use like your main wallet address that's holding all of your funds, and you can do transfers privately. So whatever token is necessary to buy the asset, you can fund it privately. That second address can do the public thing, and then it transfers it back. And then for that address B, you just never use it again. And because we're working with programmable money, in our wallet, all of this will be automated. It will be a checkbox that says, hey, do this privately, and it's going to cost you 10 cents more. And I think this kind of like gets at the heart of why we're building another wallet. Just like building another blockchain, right? We have to ask ourselves, like, why should we build another wallet? There are so many out there, right? Like, are we really differentiated? Why are we doing this? And I think it's really important to build a privacy preserving wallet because there's so much new complexity added with zero knowledge proofs. It truly is a like revolutionary technology. It's not just crypto. And to hide that complexity, to make it user friendly is an entirely new problem. And that's really what inspired us to build the Leo wallet. So you can see like a little example. We're in a private alpha right now, but you can register and we'll give you access if you like scan that QR code. And so, yeah, I think this QR code also works. And then we have another QR code here where if you want to start programming, if you want to start building with zero knowledge proofs, you can do that right now. And Pranav from the Aleo team is going to show you guys how. So that is it for me. I do have some time for questions. So if you have any questions, yeah, let's do it.
What happens when government starts?
Oh, thanks.
What happens when governments start mandating you or forcing you to report the identity of your users and the transactions they actually process?
Oh, I can just repeat it. Basically, the question is about regulation and reporting, right? So how are these systems going to work with the traditional financial models of regulation? And I will preface this by saying I am not a lawyer. This is not legal advice. But really, like, I would say this is programmable money. We can comply with whatever regulatory regime needs to be enacted, right? So if, for example, if you do a transaction and you need to generate a record on every transaction that only the government has the view key for, you can do that. You can build a system that requires identity tokens so that you're KYC'd, you get this NFT that says you're KYC'd, and then you can only exchange tokens with other people who have that. There are lots of ways to build compliant systems. The real question is, are the regulations going to be so onerous that we can't build anything useful or that anyone would want to use? right? So I think it's kind of like we can build whatever would comply, like whatever the laws are, we can build something compliant. But are the laws going to be so overbearing that what we build is not something someone would want to use?
I think what's going to happen is that the laws will be the same that apply to financial institutions. So the advantage of using these new methods would be lessened by the fact that you're burdened by all the regulations.
Yeah, so mirroring the same regulations, is likely. I think Aleo's general counsel and now COO knows a lot more about this than I do, but I think what this model is going to shift a lot of, instead of having like the company, the bank, the money transmitter as a middleman that reports to the government, individuals are going to like have to disclose, right? So if you're trying to like off-ramp money, you might have to like show some transaction history of like how you got that, right? That seems pretty likely, but honestly, it's really speculative. This is a new technology, and the government's like living 6 years in the past. So we'll see. We'll see what happens. You know, but like I think the ultimate goal of this technology and like what's something it can do new. It's the only like P2P way to send someone a dollar. So I'm really excited about stable coins on Aleo because that's like one of the key applications you can't build on like Zcash. And I think that's like, you can build private Venmo, right? And that's eventually what we hope our wallet becomes. Yeah.
I have a question. Earlier you mentioned the cost of this process, how expensive it is really, even though right now the technology has been constantly advancing, and then it's actually computationally becoming cheaper and cheaper over time, but it's kind of a journey. And you also mentioned a cost of 10 cents that you're currently pricing it. So can you maybe offer more color on, is that 10 cents enough to cover this process, or is it more like a beginning of estimation overall?
Yeah. So that 10 cents that I made up. Oh yeah. So So the question is like this process is expensive. Generating proofs is much harder than just doing things in plain text, right? Dealing with encrypted data is more computationally. And I said 10 cents. Honestly, I made that up. It's going to depend on how much the token price is, right? So like Ethereum early days, few cents to do a transaction, now a couple dollars, right? Depends on the network. In terms of like the compute cost, it's actually already really cheap, like fractions of a penny. Using the Marlin proving system. Different systems have other constraints, but it's like extremely cheap. Right now, the Aleo's in testnet 3, which is like the final testnet before mainnet, and I think it's like nearly 1 billion proofs a second that are being generated on the network. 5 billion? Yeah, so that's a lot of proofs, right? That's like more transactions. You're not going to have 5 billion transactions per second. I'll come back to you, but yeah, back there. Yeah, so in terms of like how do we get this product out there, right? Our goal is, so right now in terms of adoption, we have around 15,000 people on our wait list and about 500 people who are actively using it. I think it's a real question of like how much do people care about privacy? And I think that's a really deep question, right? I think Signal has around 200 million users. Our long-term goal is privacy by default, right? We want to have like the same user experience as Venmo. We're not going to get there with this product. This is going to be more of a crypto native product. People who are familiar with like MetaMask or Phantom, the Coinbase wallet. I think you're in the low millions to like tens of millions of users with those types of products today. Long term, I think the way you get like hundreds of millions of users is it feels exactly like Venmo. except there's no third party holding your funds who knows your social graph and everything you've done, and it would feel kind of stupid to use that product when you have this one in comparison. Cool. Yeah.
Your slide mentions machine learning a bit. Can you talk about how you would, at a high level, set up this platform as a place to execute machine learning algorithms and secret?
Yeah, so remember that zero knowledge proofs are not multi-party authorization. So like one piece of the data has to be public. Like either your data is public or the model is public. So like, let's say Hugging Face released a model that was like, give me this data and I'll give you a credit score, right? And it's like a public model. Well, in zero knowledge, you could input your data privately, get yourself a credit score without revealing like your social security, like all of your financial history, your identity even. So we see like kind of the initial adoption, like in terms of financial models, credit being a really big one. It's impossible to do under collateralized loans right now. And like some people are attempting it kind of in Ethereum, but it hasn't gotten any real adoption yet. You know, there's like Aave has like Aave Arc, which is like for institutions who've like been KYC'd, but zero knowledge proofs are going to make it much easier to like prove things about your identity without revealing that information. The long term for machine learning is fully homomorphic encryption, where you submit your data privately and the model updates itself privately, and neither the model or the data has to be public.
And you're saying that's not possible right now?
So it is possible, but it's like, it's so slow that no one uses it for, like, it's just easier to get data for free and like pay people for their data than pay for, yeah, like I heard someone say there like aren't enough GPUs to like use Chat GPT for Google, like not enough GPUs in the world, right? To imagine like a scale of like at least 1,000 to 1,000,000 times more, right? It's just not like feasible for large companies to use homomorphic encryption. Yeah.
When the SEC decides what the KYC, AML compliance regulations will be for crypto, it's going to cost between $1 and $5 per customer, per user to actually verify that data. Where do you recover that cost from?
Like, how does a wallet make money?
How do you pay for the KYC, AML process of each user?
Yeah, so the question is, how do you pay for KYC, AML? Centralized exchanges already do that, right? So it's like part of their cost of customer acquisition. It's actually a pretty low cost. They spend way more money on ads. Yeah. Right now, no, right? So it's in a test net, so like you can't get, the tokens are just for like development purposes, right? They're not like, they don't hold any sort of economic value. Ideally, when it gets launched, it will be like listed in exchanges, centralized, decentralized. Someone on the Aleo product team could answer like listing way better than I could. Yeah.
Let's take one last question.
Can you talk about your backend
Like the backend for Aleo. So Aleo is written in Rust. It runs on GPUs and CPUs. There's this, so the question is like, what is the infrastructure for Aleo? There aren't ASICs right now for Aleo, but people are working on them. There's also this really cool thing called the Z Prize. And the Z Prize is a bunch of different privacy companies who have come together to just create like prizes, like $1 million here, a couple $1 million here for various improvements. The operation that needs to be optimized is not like a SHA-256. It's called a MSM, a multi-scalar multiplication. And basically, if we can make those really fast, if we can create hardware chips then it's going to be even easier and cheaper. Something that a lot of people don't kind of realize is that chips didn't actually originally include like optimized versions for today's encryption. Encryption, when it came out in 1994 with the introduction of SSL, was actually really expensive and slow to like encrypt all of your internet traffic. I don't know if you guys like use like modems, it was so slow, and to like make it slower, right? But without that technology, you wouldn't have like credit card payments or banking online. So, kind of like the long future hope is like you get deals with like Intel, AMD to like integrate these to make them really, really cheap, but you're going to have to get a lot more adoption first. Cool.
We had an injury, so you'll have to bear with that.
Hey, thank you.
Are you skiing with Howard?
No. No. So, all right. Yeah. Just put in lapel. Yeah.
Hi, everyone. My name is Pranav. Yeah, thank you, Evan, for motivating zero knowledge proofs. So what I'm going to hopefully do is give you guys a taste of the tools we've built at Aleo to make writing zero knowledge proofs using our platform easier. Before I get into it, can I get a show of hands who's worked with any smart contracting language, deployed a program before? Sweet. And who has worked with any like ZK framework? Anything like that? Anything related to ZK? Cool. All right. Now that we have a baseline, yeah, let's jump into it. So I realize we don't have all of our laptops out, but here's a link. It's pretty easy, bit.ly/start-aleo, which takes us to our developer docs. There's a bunch of resources on there, but for the purposes of this talk, like, we don't need it. We'll just kind of jump into some of the code. So one of the things that we built at Aleo is a language called Leo, which makes writing zero knowledge proofs, specifying your programs much easier. In the previous talk, we had some good motivation for why we want zero knowledge proofs, but the kind of challenges and the challenge that I've faced is how do you actually, write a program? How do you actually prove something, specify something that you want to do privately? And that's one of the big challenges that we face just in general in the ZK space. So to make that easier, we've built this programming language called Leo. It's a high-level language that compiles into an intermediate representation that we also designed called Aleo instructions. And that intermediate representation gets serialized into some bytecode. So some standard compiler architecture to really just make this experience easier. For the purposes of this talk, we're only going to talk about Leo. Everything else, you can find some more resources on our website. So with that, we'll just jump right into it. Look at some code. So Leo has 16 primitive data types. Some of these are probably familiar to you guys from other programming languages. You have integers, booleans, and then you also have algebraic data types. And these are more specialized to the cryptographic primitives that we have underneath, the cryptographic primitives that relate to zero knowledge proofs. We also have some specialized data types like addresses, what blockchain wouldn't, what blockchain doesn't have this, So we make this programmable. And yeah, with that, we also have some custom data types, user-defined data types. There are two, the first of which is a struct, and this is just structs that you see from other programming languages, composite data types that you can define with different fields. Pretty straightforward. So with that, just super fast introduction, let's actually look at a Leo program. So what we have here is a program, hello.aleo. We define a function foo, and then we also define a transition. So this is a programming concept that we've introduced. A transition essentially forms the public interface of your contract. Functions are effectively helper functions that can be called internally, but cannot be called externally. And for people coming from Solidity, you're looking at stuff like internal and external, and that distinction. So that's one concept that we've kind of introduced. Another one is type systems. So Leo is strictly typed. Actually, at the moment, you have to declare types for pretty much everything, any variables that you declare. Now we're working on type inference, but for the moment, we kind of went with this decision for safety and really to strictly enforce good programming in a sense. Leo is also has some primitive default arithmetic operations. The way Leo works under the hood is that all operations are safe by default. So they check for overflow. If you just use the standard primitives, you can't have any of these overflow errors, division by zero errors, so on. Now, if you want to use wrapping operations, these are also available to you. But all this sort of information is included in our docs. So before I kind of just jump into more code, does anyone have any questions about anything I introduced? Great. All right, let's keep going. So one more thing I forgot to cover here is that within a transition, which your public interface of a contract, Leo also lets you define variables that you declare as public and private. And the way this works under the hood is that once we compile this program and compile it into a circuit, into a program that is representable in a snark, the outputs of this program are essentially encrypted whenever they're produced and put on chain. So basically, users have this ability to control visibility with at a very fine-grained level in Leo. Cool. And then kind of jumping through some things. So as you'd expect in any programming language, you have conditionals, you have early returns, basic control flow. You have for loops. In this case, since Leo is strictly typed, you have to type your variables here. And then for the moment, Leo only allows literals, integer literals as your loop bounds. And this is kind of a specific thing that comes about with snarks and the way circuits work. The reason is that when you write a program that needs to be expressed into an arithmetic circuit and then converted into a zero knowledge proof, you need to ensure that program is finite. It can't be an infinite program because you have to eventually terminate for you to actually generate a proof, and you have to terminate deterministically. So for that reason, Leo only allows integer literals. Now you can do some fancy compiler tricks to actually get more expressive loop structures, but more to come. These are updates that we're also looking at and investigating for users. And then you'd expect some assertions, and I kind of rushed through this, but these are some primitive building blocks that Leo has. And we're hoping that when we design this, that it's familiar for users. I feel like the way I kind of describe it, it has a Rust or TypeScript-y like feel. And yeah, that was our main kind of motivating principle here. Now, before I get into some more concepts about actually programming on a chain, with zero knowledge proofs, anyone have any questions about Leo, its simpler features? Way in the back.
You mentioned with the CK stars, homomorphic structures, right?
Mhm.
The manifold. So if this is ZK stars, exactly what you're saying. Leo's written in literals, right? So how does that work with the manifold structure of a homomorphic program. Because it's meta, it's in and of itself, right? That's what homomorphic means. It's a manifold. So if everything has to be literal, conceptually, it's a complex. And if you're creating transactions, right? Publishing these transactions from public to private, right? I imagine it would be security embedded code.
I'll say, I think that we have some stuff to unpack to kind of go into it, but I'd like to hear more about it. So maybe after we could kind of chat. Yeah, great. Yeah, some more. I think there's some more I need to unpack to understand that question. Great. So with that, Leo also offers some more powerful constructs. And these things are actually fundamental things that are needed when you combine ZK with on-chain state. So for people coming from Solidity and just general like programming models in the blockchain world, one that we're most familiar with is the account model. The account model essentially has accounts for programs for users, and all your data, all your programs data and state is directly associated with an account. Now, for reasons that actually get pretty technically involved, and there's some great resources for this that I can point you to, the account model is actually broken in terms of privacy. You leak tons of data whenever you, actually like Evan motivated earlier, like whenever you interact with a contract on Ethereum, you leak access patterns, you leak usage. So for that reason, we had to depart from the account model and approach something new. And this is called the record model. The record model is essentially a way of segmenting application state into individual packets or individual records. Each record has an owner, a gates, and then a number of user-defined fields. So owner and gates are the two required fields. And with the owner, an owner of a record is the only person who can decrypt or use a record on our chain or on the blockchain. So it ensures users have kind of sovereignty over their data, and no one else can read their data that is associated with that application. Gates is a subdenomination of Aleo credits. It's essentially, you can think about it as cents is to dollars as Gates is to Aleo credits. Cool. So with this kind of primitive, we encode application state. Users exclusively own their records. And because the state of an application is sharded across a number of records, this model allows for concurrency. And it's sort of fundamental to making privacy scalable. So with the records, you can kind of combine them with other things. You can combine them with other composite data types and build more expressive programs. But what I want to do is quickly show you how records actually work with our ledger, how the model kind of all fits together. So let's say you have a transition foo. A transition, again, which is the public interface of your contract, can take some number of records as input and produce some number of records as output. Now, how does this sort of work with, let's do token transfers as an example. So we have a program, token.aleo, and token.aleo defines this record token. Same definition we saw before. There's owners, gates, and balances. So the token program also defines a program or a transition called transfer. So let's kind of like go through and unpack this. So transfer takes in a sender, which is a token record, the token record associated with the person trying to send some money, a receiver's address and an amount, and then produces two token records. In this case, you see that there's no like visibility modifiers on any of these things. And in this case, like Leo is private by default. So if you don't put anything, it's assumed to be private. So in the first line, or second line, line 2, we calculate the difference, the amount that the sender is going to keep. Since Leo is safe math, like by default, this operation will error on overflow. And then from lines 3 to 7, and then 8 to 12, we produce two new records. One containing the balance that the sender keeps, and one containing a token record containing the amount that the sender wanted to send. And then we return these two records. People familiar with like the Bitcoin model with UTXOs, this will look actually very familiar. And records are essentially, you can think of them analogous to UTXOs, and the programming model is very similar. So how does this all work on chain? Some stuff. Okay, cool. So so let's say we have a ledger, and Alice wants to send some tokens to Bob. So right here we have a record N. Alice is the owner. There's 0 gates associated with the record, and she has 10 tokens. And note that like this record is encrypted under Alice's address. Only Alice can read this record, and only Alice can use this record. You know, basically whenever she invokes transitions and whatnot. So when Alice wants to send some money to Bob, she's going to invoke a transition transfer. She's going to provide Bob's address and the amount that she wants to send. And this transition is essentially run off-chain. So what she does, she runs this whole thing off-chain. It produces 2 new records, one containing Alice's remaining balance that's encrypted to Alice's address, and one containing Bob's new balance encrypted to Bob's address. And then she also produces a proof that this transition was executed correctly. Now she takes that whole thing and submits it to the network. And if the network accepts her proof, if her proof is valid, the network adds the 2 new encrypted records to the ledger. And notice how like the old record is grayed out. In the record model, once you consume a record, you can't use it again. And then and basically the protocol enforces this. And this is to ensure that you don't have double spend attacks to programs. So essentially, the network sort of marks a record as consumed, and it cannot be used again. So this is the record model. Before I go any further, anyone have any questions? Yeah.
So is it publicly visible that the nullifier or whatever is consumed, or actually do you not know which?
So you produce it. Oh, so the question was, is the nullifier that's published publicly available when a record is consumed? Is that right?
Yeah.
The nullifier is publicly available, but from it you can't tell the data of the record that was consumed. You can tell that like there's essentially, when you publish records to the ledger, there's some commitments that are stored. The nullifier essentially corresponds and tells you which commitments for which records have been spent. But you can't reverse engineer what the records were. Over there.
Any hands up on tokenomics?
Oh yeah, the question was any heads up on tokenomics. Honestly, this is still some unexplored stuff for us. Right now, we're just kind of designing these core elements of the protocol. We're really hoping that the community kind of participates and helps us figure out how this whole thing looks like down the line.
Sure. It's an interesting technology.
Yeah.
Asking developers to commit anytime, even considering looking through the code, looking through the docs, and we don't even know what the tokenomics are. 3 months down the road, we find out you own 50% of tokens. It's just not something that appeals to developers. It's kind of like what's there.
I understand your point. I think there is more to, like, I'll say, like, I probably can't comment too much because I don't know too much about how token distribution is going to work in terms of exact percentage allocations. But the general goal of our project is to make it accessible to developers and have the devs own, take ownership of this thing. Maybe someone else can comment from the Aleo team here, but maybe we can also chat some more about it afterwards as well.
Come find me after. We can talk about
Yeah, Sam's got you. Yes, I saw you in the back over there first.
A little bit different question, but how does the gas fee work in this kind of programming model?
Right. So yeah. So the question was, how does gas fee work in this kind of programming model? So really, like in some sense, like the pitch is that there is no gas, and there's some subtleties to that sort of answer. Since the fee is essentially proportional to the time it takes. There is sort of like an implicit fee, but these fees are essentially only fees that you give for transaction prioritization when you submit transactions. Because every single transaction to verify its proof is constant time. There's no distinction between like the amount of computation you do. In the way Ethereum it works is that the reason why you have gas is because you need to pay per opcode executed. That sort of model kind of disappears. So there's only like a fixed flat cost associated with the amount of like, you know, data you're sending, which is also constant in size.
If you want to generate your proofs yourself
You can,
and mine your own blocks, it's nothing. There's no like, you're not paying per like computational execution that you're doing the same way that you are in Ethereum.
any more questions? Yeah, so the question was, is the verification constant time? And yes, it is. Over here?
I'm now curious about the market. If I launch a token on the blockchain, what's the verified marketplace going to look like? Is this something that's able to work with AMAs, or how would the pricing work with tokens or listing?
So the question was like, how does the marketplace around like deployed tokens and assets on chain look like? This is stuff to still be built. Different. Yeah, it's not this. It's not really the same model because I mean, just fundamentally the constructs are different. But yeah, I think in my opinion, there's still a lot to be explored.
There will be markets. They will look different than they look on Ethereum.
Yeah. All right, great. Oh, great. I think it's how much value is it to your consumers or to your you know, to your clients for privacy? Suppose you're a merchant selling drugs on Silk Road. It might be more valuable. But let's say, you know, you're just selling, you know, some food on a stand on the side. Probably not so much. So I think it's really dependent on your use case. Yeah, I don't know if I should have used that example, but I might get in trouble for that. But exactly. Yes. Yeah. Any more questions? Great. Over in the back.
That the transition is calculated offline.
Yes.
So what state is required off-chain? Do I have to have a copy of the state?
Right. So the question was, since the transition is calculated offline, what state is required to actually run this transition? And the state is the records themselves. So when you run the transition off chain, you need to put in some, if your transition requires some records as input, you need to sort of provide those records in to that transition. And you can do this by querying the chain with your address. And with your address, you'll only be able to get the records that you own yourself. So the pieces of state that you own. Follow on? Yeah.
So like I get the state of the transition from the chain itself. How do I authenticate with the chain? Very complicated. I'm talking to Google, I have this like I have to get the state from the chain. What is the state?
So, oh yeah. So the question was, the following question is like, how do you authenticate with the chain? How do you know that you're getting the right state from the chain itself? I think this question you can kind of unpack in a lot of different ways. One way is like just in terms of user experience is usually you'll have some wallet or management software that's going to keep track of your records for you, so that you kind of know what stuff you have, you know, out there. In some sense, though, like it's always possible to do like a network isolation attack where you isolate like a bunch of adversaries isolate around your node or your party and then kind of just trick you with bad state. And as long as they can maintain isolation, you're kind of sort of screwed until you can break that effectively.
What is the way to get the state? Web address, how do I
So like each node like opens like, you know, RPC endpoints, and you can kind of query those. And some nodes will choose not to, some will, and yeah, that's how you can kind of query chain.
Isn't it part of what they're asking?
Yeah.
But how can we trust it
Yeah, so I mean, at some level, oh, so the question was, how can you trust the data that you got from the chain? So like when you query the chain for your state, for your records, how do you know they're actually yours? Um, so kind of to simplify this question, I'll say that, okay, let's assume you're running a full node that is connected with the network. Um, Essentially, the way you validate that is that you check that like, your record is effectively, when you kind of like digest it and produce a commitment for that record, for that raw data, that it corresponds to a commitment that is stored on chain. And that's how you know it's correct for,
Like a vertical inclusion.
yeah.
Same way it- almost identical to how it works on Bitcoin. It's a proof of work.
So I interpret that question as something related to that terrifying Zcash problem with minting. There was a bug where somebody could have minted however many coins they wanted and nobody else on the chain.
Yeah.
Is that right? So there's a signing ceremony, I guess, that already happened.
So there is no signing ceremony. The way we do it is we sample these parameters with a setup ceremony that we've done, called the Powers of Tau ceremony. And this is like a publicly, like open to everyone ceremony that we ran, I think a couple months ago.
It's perpetual powers of Tau, meaning it's a thing that's kind of ongoing. So you can continue to add entropy to it, like into the future. So it's not like it was happened way in the past and you're never going to be able to experience it. It's like, oh, I just joined now, I want to be able to enter it. I can contribute in that.
Yeah, so at the time we ran it, it was the largest setup ceremony that was done. And basically, as long as there was one honest party in that, we're good. And it wasn't just a secret ceremony that was done behind doors at Aleo. It was just open to the public. Cool. With that, how are we doing on time? Okay, cool. I'm just going to introduce something, a feature that I'm excited about. That's sort of going to make everything I kind of said a little bit more confusing. But it's important to this programming model because at the end of the day, we want some sort of combination of privacy and usability. And this concept is essentially mappings. So for people who are familiar with Solidity, mappings are pieces of state on chain that map from keys to values. Generally, the concept I'm trying to introduce here is on-chain state and how we're going to instantiate that at Aleo. So these are an experimental feature that's available in Leo right now. You have mappings, straight key value pairs. And essentially, the way they work, before I go into this, the way they work is mappings are pieces of on-chain state that you can interact with when you run your transition and submit it to the chain for execution. The way it works is you run your transition locally offline, and then once your proof gets accepted by the network, you specify some number of operations for everyone in the network to run. These operations should be assumed to be public, so you shouldn't assume privacy for them. But it's a great way of maintaining and coordinating on state. And you need to use this for stuff like escrows, any sort of like public revealing of data, oracles, this could be useful for. There's a whole number of applications where this kind of comes into play. And so here we have a transition transfer, but this is going to do something a little bit different. What we're going to do is we're going to transfer some amount of tokens that I have privately in a record and update it to on-chain state and publicly, transfer this money to another party. And the way we do this is we have a private record sender, we have a public receiver, an address that we want to send to, and a public amount. So this stuff everyone will know on the network. I'm going to first compute the difference, the amount that's going to be left to me, the remaining tokens. And then I'm going to invoke what we call a finalized block. And so a finalized block essentially is a sequence of instructions that you can specify to be run on chain after your proof is verified or your transaction's accepted by the chain. And what this lets you do is lets you kind of do some pretty cool like private, like hybrid private and public programming essentially. So what you can do is you specify, finalized block, and then just invoke it after you return with a then finalized keyword. And there's more documentation on these operators online. But let's kind of look at how this works. I think a visual example here will kind of demonstrate that. So we have a network with a couple of validators. There's a ledger with Alice's record encrypted to her address, so this is still private, with 10 tokens to her name. Now Alice wants to send some money publicly to Bob, and what exists on chain right now is a mapping of tokens that Alice and Bob have. Right now it's both 0. These are public tokens. Now Alice already has 10 private tokens, but she has 0 public tokens, and that's sort of the distinction. There's kind of 2 elements you want to track if you want to get the sum total of tokens. So the first thing Alice does is she queries the network for an encrypted record. And then once she has the record, she executes the transition transfer, the one we just talked about locally. And to that transition, she puts in as input Bob's address, the amount she wants to send, and that transition produces Alice's new record. This is a private record containing her remaining balance, and then just pushes through the Bob's address and the amount she wants to send, and then also includes a proof of the transaction. So she packages that whole thing up into a transaction. So you have her record, you have the amounts she wants to send to Bob, and the proof. And if the network accepts her proof, then they add the record to the chain, and then also update the mapping with Bob's new balance. And essentially, with this hybrid model, you can do really cool things, right? Like, so Alice was able to keep the amount of money that she has private, but publicly, release some money to Bob that Bob can use and the whole network knows to spend with. And we're still experimenting with this feature. Actually, Demox has been driving a lot of the use case and the development there. And more to come as we approach mainnet, but I think this is going to be a pretty exciting way where you kind of get the best of both worlds, because at the end of the day, like on-chain execution, the way Ethereum does it is still useful. But zero knowledge proofs are useful as well. So we decided to kind of combine this model and experiment and see what we can get out of it. So just quick stuff. There's some software out right now to deploy applications and spin up your own like local node, test out your programs. It's pretty cool. Really recommend you guys try it. We also are doing some formal verification work with our programming language and our stack. So there's a bunch of stuff that, in the interest of time, that I will kind of gloss over. But if you're interested in formal verification stuff, please find me after and talk your ear off about it. And yeah, so let's wrap it up. So Aleo, it's all open source. We have a workshop repo if you want to get your hands into, if you want to try using Leo programs. And yeah, find us on Twitter and Discord. We're all active on there. Ask us any questions. And yeah, thank you all for listening. I hope you kind of got a good idea of what Leo has to offer.